All right, welcome back. So I have a few announcements for you first, logistical things. So this morning I posted homework 1, lab 1, and the ComCloud primer. Okay, homework 1 is due next Friday, so not tomorrow, but a week from tomorrow, 5 p.m. There's a Dropbox set up in the big, everyone knows where the Dropbox array is over around the corner in Phillips. So there's one for this class. I think it's one box for 467 and 567. So just put, for both classes, just put it all in that one box. So that's where you submit stuff. There's lates are possible, late submissions are possible. That's explained in the policy document. So homework 1 is due a week from tomorrow. Homework 2 is due 2 weeks from tomorrow. The lab 1, I don't view it as like a 2-week-long project. It's more just like to give you extra flexibility in terms of when you do it, So those are both up. There's a primer up there on how to use the ComCloud server in order to do the lab, in order to do this lab and all the subsequent labs. There's also the Python code that we use to send the WAV files back and forth. So the Python code you use to send your WAV file to the server and then get it back. That's up there too. It's explained in the primer. I mean, that stuff's installed on the ECE Linux cluster. So you can just log into the ECE Linux cluster or use the 314 Linux lab up here in Phillips to communicate with the server. Or if you want, the Python code that we use is just available to you. You can put it on your own laptop and then run it there. And they don't need any of the ECE machines involved at all. You can just do it directly from your laptop wherever you are. So my plan that I announced on Tuesday was to spend tomorrow's recitation going through how to access the ComCloud server. Like I just kind of walk you through the process just with my laptop connected to the display, and then show you how to send a WAV file through, get it back, and so on. That's like the logistics for the lab. I can still do that. On the other hand, I'm also learning about the different capabilities of Blackboard, okay? And it's possible for me to just record the whole thing on my own computer in my office and just post a video on the Blackboard site illustrating that same stuff, okay? There's advantages both sides of this. If it's recorded, you can come back later and look at it. If you can't come tomorrow, whatever, you can easily see it. On the other hand, it's not a live thing. It's just pre-recorded, so you can't ask questions there, on the spot. You'd have to, put it on Piazza or whatever. So I'll just take a quick vote. So who would prefer that I just show up and we do this live tomorrow during the recitation? I hook my laptop up, I walk you through it, you ask questions. Who would prefer the live version of this content? 1, 2, 3, okay, hold your hands up high actually. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Okay, that's almost certainly majority. Who would prefer the video form of it? Uh-huh.
Can you just record the live session tomorrow?
Not easily. I mean, it's rather simple for me to sit in front of my own computer and just, use the camera and the screen capture. I don't know. I can try. There's no guarantees though. If we're doing it live, there's no guarantees it's recorded. Yeah. All right, so I'll scrap the video version of it. And so that'll be the recitation tomorrow. It'll just be me walking you through how to send files to and from the ComCloud server. I doubt it will take a full 50 minutes to do that, but I guess you never know. And last announcement is to join the Piazza site. That's what we use for our, offline in the sense that it's not during class, offline discussions, online in the sense that it's, electronic. Blackboard, of course, you get enrolled automatically when you roll in the class. Piazza, at least the way I have it set up, doesn't do that. You have to join the Piazza site. So there are instructions in the policy document for how to join the Piazza site. It's just a web page you go to. All right, that's all I have. Any questions? Okay, so I didn't quite finish the course overview on Tuesday. I have, maybe like 5 minutes left of stuff. So we'll just finish that, and then the main topic for today is random vectors. So this is where we left off, and let me announce a convention here at the beginning. Okay, so anything I write, except for the announcements and the plan for the day, anything I write on the board before lecture starts was stuff that was up on the board during the previous lecture. Okay, I'll never write anything new before lecture starts. Okay, so if you're at the previous lecture, you don't need to recopy anything that's up as you sit down. Okay, I only add new content, after 125. Okay, so this was up, at least it was a piece of a diagram that was up from Tuesday. So I said I wanted to describe, in some sense, the problem we're trying to solve and the solution that we're going to use. Okay, and the problem that we're going to solve in this class is just how to move bits over a channel. Okay, so you're given some physical medium like the RLC filter in the COM cloud or a fiber optic cable or a piece of spectrum or whatever. So you have a physical channel, and our problem is to just move bits over that channel. So take a bit stream, encode it into some waveform, some input that can go over the channel. The channel will distort it in some way, shape, or form. Okay, it'll come out, and then we're going to design another box that's going to take the output of the channel and then try to recover the bits. Okay, we're going to try to maximize the bit rate here. How many bits per second can you push through in a way that you can still recover them at the other side? That's the problem we're trying to solve in this class. This is part of a much larger problem where you're trying to move content like videos, speech, images, whatever, email. Okay, and we've reduced that problem, just the problem of moving bits. Okay, and Shannon separation theorem is what allows us to do that. We're not going to say any more about that problem from here on forward. We're just going to focus on this problem here, moving bits over the channel. Okay, so that's the name of the game for this class. Just how do you move bits over a channel like this? So the solution is in a word or in an acronym. It's OFDM, which stands for orthogonal frequency division multiplexing. Okay, and OFDM, as a term, encompasses kind of a few different concepts. The high-level idea, you can describe as follows. The high-level idea is that if your channel takes the form of an LTI system with noise added on top, then a certain type of signaling scheme is particularly effective. So if your channel takes the form LTI system or LTI filtering plus noise, then I'll say one should encode the bits that we're trying to send. In the frequency domain. As opposed to the time domain or some other domain that no one's thought of before. So it's particularly effective to encode the bits in the frequency domain when your channel takes this form. So this is rather vague. I haven't really said exactly what I mean by LTI system plus noise. All this we'll make precise later. I just want to kind of give you a flavor of what's to come. This is a bit reductive. I mean, OFDM involves things like the cyclic prefix and stuff that we'll talk about in detail. I'm not describing that here. So this is not really the complete picture. It's just kind of the basic idea. So OFDM, this basic idea along with the particulars like this prefix and so on is used all over the place. Many different communication technologies use this. Essentially nowadays, any channel that takes this form, people use OFDM, and lots of channels take this form. Pretty much any channel doesn't have like a strong nonlinearity in it, takes this form. So it's used in, for example, DSL, digital subscriber lines, cable modems, not the early ones, but the later versions of cable modems use it. So almost surely the internet that you have in your apartment is using DSL, or your house, or wherever you live. I don't know, I guess there's like fiber in Collegetown, right? Do you guys have fiber going to your apartment? Fiber optic cable is not, there's actually often nonlinear effects that arise there, so OFDM is not used directly there. But anyway, cable modems, DSL, it's using Wi-Fi, it's using LTE, so your phone is using OFDM. What else? The European digital TV standard uses OFDM. The US one does not, for interesting historical reasons we can talk about later. The Sirius satellite radio, they have ground repeaters. Okay, so I mean, the downlink from the satellite is not OFDM, but in certain like dense urban environments, apparently the satellite operators install these ground repeaters because when you're like in Manhattan, you can not have a good line of sight shot to the satellite because there are buildings around. Okay, so the ground repeaters, like the channel from the ground repeater, to a typical receiver, does follow this LTI plus noise model, and so Wi-Fi or OFDM is used for that. Okay, so bottom line is, like, if you understand how OFDM works and why it's used, okay, then you understand like a relatively large swath of the landscape of commercial communication systems and why they're designed the way they are. Okay, so that's the problem. That's the solution. On one board. That's kind of where we're headed. Let me give you just a quick outline of what we're going to cover between now and the end of November, and then we can dive into random vectors. Okay, so we'll start with a probability background unit. Okay, what I nominally plan to cover here is a section on random vectors. That will start today. Okay, and a section that we probably would get to maybe like next Thursday around that time on Bayesian inference, Bayesian detection, more precisely. Okay, so that'll be the probability background. Okay, then we're going to do a signals and systems background. I'm going to call this the linear algebraic approach to LTI systems. Okay, and that'll be all the review. That'll be all the background. This is my nominal plan for the background, and let me say just at the outset that in my experience, like, one of the most challenging parts about teaching a 4,000 level class is trying to figure out how much review to do, how much background to cover. And I can say from experience, I've messed it up in both directions in the past. When I first started teaching this class, I did like a really thorough review to make sure everyone had a really solid probability background, everyone understood the LTI systems theory we wanted to do, and I got complaints that the class got off to a slow start. We didn't spend enough time doing interesting digicom stuff. We spent too much time kind of rehashing, 3250 and 3100 and so on. So I said, okay, I can fix that. so I fixed it, and then I got complaints from I would say panicked students who said, like, we don't understand all this stuff you're assuming we know. Okay, so I think I've kind of found a kind of a median path here. My plan is to do a review, but kind of zero in on the parts of like probability and LTI systems theory that we will use especially a lot and are often not really emphasized in the prerequisite courses. Okay, so you probably worked a lot with random variables. We use a lot of random vectors. Okay, so I'm going to talk about that. You probably did some basic hypothesis testing or whatnot in 3100. You may or may not have. We're going to use it a lot in this class, so we'll zero in on that. And then there's a particular way of thinking about LTI systems in terms of matrices and linear algebra, and so I'll zero in on that. I'll say I've learned though that like there's no like right amount of background to cover, in the sense that like every student's different, and what's perfect for you is not perfect for you, and so I have to chart a kind of median path that like makes no one happy, but no one like is really irate either. I've also learned this is a moving target, so like I think I got it right, and then the next year I find it's way off because the students are not the same year to year, and the prerequisite classes are not the same year to year. Okay, and coverage varies 3100 say from year to year. So anyway, this is my nominal plan, but this part is in particular is for your benefit. So do give me feedback if you think it's too fast or too slow or assuming too much, whatever. Okay, so that's the background part. So you can look at the lecture schedule on the Blackboard site to see when that will be done. It's not like over much review. I don't know off the top of my head when that's done. But when that's done, you can start kind of the course material proper. And we'll start with just a unit on how to model the channel. Like take the ComCloud channel. You know, you have a WAV file, it gets played through a sound card, it goes through an LC filter, it's recorded by a sound card, you get another WAV file. Okay, so end to end, WAV file to WAV file. Okay, how do I model everything that happens in that whole chain? Okay, all the amplifiers, all the filters, the ADC, the DAC, the DAC, okay, the filter, the cables, everything. Okay, how do you kind of model that succinctly? And how do we get like a nice math model for that whole system that we can then analyze? Once we have that, we'll start talking about communication. And I like to start simple and build things up step by step. So we'll start by looking at communicating over channels that are kind of simplified compared to what we have to deal with our channel. So channels with, it's my abbreviation for width, by the way, W/. So with noise, but without, there's my abbreviation for without something called intersymbol interference. So intersymbol interference is a term I'm not expecting you to know now. This is a term we'll use a lot in the class. We will define it later when we get to this part. Okay, once we understand that, then we'll look at how to communicate over channels with noise and ISI. All right, we'll talk in particular about OFDM. All right, we'll talk about some of the like kind of really nuts and bolts stuff required to get all this to work on, you know, on a real system, like synchronization and learning. So how do you learn like what the impulse response of the channel is? Like how do you figure that out? Because no one hands it to you. You know, all we have is this this server. You can send waveforms through. So how do you learn that? How do you synchronize the transmitter and receiver? So nuts and bolts, stuff like that. All right, at this point, you'll know everything you need to know to do all the labs, pretty much. Okay. We will have a couple of units after that. One is on coding, which is like how to map bits to waveforms in a way that can be recovered easily. And then the last unit will be on wireless systems. Okay, so how can we map everything we learned from communicating over the ComCloud to wireless systems? Okay, so I guess I should be more precise. So up to this point, you can do all the 467 labs. Okay, in the last 567 lab, we'll use some wireless here. Okay, so that's where we're headed. So we'll start here, and then, you know, by the week after Thanksgiving, finish that. All right, are we good? Any questions? All right, let's get to it. So this is the probability background. So again, there are two parts to this. I'm going to zero in on random vectors and talk about them quite a bit, and we'll talk about Bayesian detection, like the two parts, you know, of basic probability that we'll use a lot and that may or may not have been emphasized in your prior probability class. Okay, so we'll start with random vectors. Okay, so presumably you used random variables extensively in a prior probability class. You're pretty comfortable with them, hopefully. We work with random variables a lot in this class, but we tend not to work with one random variable in isolation. We tend to operate on like a bunch of random variables at once. Okay, so for instance, one of the exercises in lab 1, okay, is to just send silence into the ComCloud server, send silence into the filter. So just like a set of 0 samples, and just record what the receiver hears. Okay, the receiver is not going to record zeros if you send in zeros. Okay, because there's noise in there. It's basically going to record the noise. All right. So you'll get a WAV file. A WAV file is just a collection of audio samples. You can bring MATLAB. It becomes a vector. Okay, MATLAB is just a vector. So you have a vector of audio samples. You're sampling at 44.1 kilohertz 44.1 thousand samples per second. So you run it for 1 second, you get a vector with 44,100 samples in it. Okay, and they're random. Okay, because this is a realization of the noise that the receiver heard. Okay, now that noise is going to be a major impairment for in our ability to communicate over this channel. So we need to understand the noise, understand statistics, how it behaves, how to prevent it from messing things up too much. Okay, and so we need to kind of understand that noise vector, its properties and so on. And it's helpful to think of it as a vector because then you can apply linear algebra techniques to it to analyze it. Okay, so we tend to have lots of random variables in play at once in this class, and we find it convenient to put them in a vector. I guess I go like this for a vector, really column vectors, right? So it's helpful to put them in a vector, think of them as a vector for the purposes of this class, just to facilitate analysis. Okay, so that's why I'm going to zero in on random vectors. Let's start with the definition. Okay, so a random vector is simply a vector whose components are random variables. Here's the notation that we'll use. Okay, so we'll write it like this. X consists of x0, x1, up to say xn minus 1. Okay, so a few notational conventions here. An arrow like this means vector. Okay, capital means random. Okay, we'll use the square bracket for indexing. Okay, which I know looks a little notation heavy at first, like when I do like x sub 0, x sub 1. The reasons for doing it this way, and it looks a bit excessive, but well, that's the way we'll do it in this class. And we do like C instead of MATLAB indexing. Okay, so we start with 0 instead of 1. Okay. Okay, so you can think of this as like, the vector of samples that you got at the receiver when you sent in silence. The first sample, the second one, and then the 44,100th sample at the end. All right, a random vector is completely described by the joint distribution of its constituent random variables. That joint distribution can be described in many ways. The most general way is to give the joint CDF of all of these constituent variables. Cumulative. Okay, so the cumulative distribution function, abbreviated CDF, of a random vector x is, I'm going to write it like this, f sub x evaluated at little x. Okay, so keep in mind the notational conventions here. Arrow means vector. Uppercase is random. Lowercase is like a realization. Okay. And by the way, I try to put a little hook on my lowercase x's so they're easily distinguishable from the big ones. I try to. Okay, sometimes I get kind of excited as I go and I miss the hook. So feel free to ask me if it's not clear what case things are. Okay, so this is defined as, it's just the joint CDF of the constituent variables. Okay, the CDF of the vector is defined to be the joint CDF of the constituent components. Okay, so this is the chance that x0 is less than or equal to x0, and x1 is less than or equal to x1, and so on, through xn minus 1 less than or equal to xn minus 1, like that. Okay. The CDF of the random vector completely describes it, okay, and that if you have this object, if you have this function, and you can evaluate it for any x, okay, you can compute any probability you want involving this, this random vector. Okay, so once you have this, you're good to go. This is like a complete object in the sense that it completely describes this random vector. Any probability you want to compute involving this x, you can compute from this. It might be painful. Okay, it's not necessarily easy to compute stuff from the CDF. You've probably experienced that in an earlier probability class. Okay, but in principle, it's doable. Okay, given how awkward it can be to work with the CDF, people typically work with other objects that contain the same information that are easier to work with when possible. So one example of that is the probability mass function when x is discrete. Okay, so if x assumes finitely many values, okay, then we say x is discrete. And we define this probability mass function. Or PMF is, okay, so you just like, evaluate the probability that x takes each of the different finite values that it can take. So the chance that x, I guess just write it like this, right? The chance that the random vector takes this particular realization. You can also write this as like the chance that x0 equals little x0 and x1 equals little x1 and so on. Okay, this is also complete in the sense that if you have this, you can compute any probability you want. Okay, so if you want to know the chance that x falls in some set A, where A is a subset of Rn, is just going to be the sum over all little x's that are in A of the PMF evaluated at A. Okay, and you probably used formulas like this for random variables before. We're doing it in the random vector form. Okay, so there's one special case where you don't really need to work with the CDF. You can work with something that has the same information but is a lot easier to work with, the PMF. Another example we can do that is when x is continuous. Okay, so if the CDF of x can be written in the following way. Okay, suppose I can write this thing as an n-fold integral of some function that we'll call little f sub x. I guess this is a dummy variable of integration, so I guess we need like a prime there. Okay. Suppose this is true for all x. This is my abbreviation for all. I mean, it's not mine, I didn't invent it, but this is the abbreviation we'll use. If that's okay. The for all x. Okay, if that's true for all x, for some function little f of x, then, so punchline up here, two things. You say x is continuous, and that function f is called its probability density function. PDF. Okay, so in general, the blah of a vector is the joint blah of the components. Okay, so the CDF of the vector is the joint CDF of the components. If the random vector is discrete, then its PMF is just the joint PMF of the components, and then if the random variable is continuous, i.e. its components are jointly continuous, okay, then its density is the joint density of the variables, okay? Have you all worked with joint densities of random variables before? Yes? Yes? Okay, good. All right, in the continuous case, the density contains exactly the same information as the CDF. Right? And clearly, if you have the density, you can get the CDF. Moreover, if you have the CDF, you can get the density by just differentiating, right? You want me to write that out? And we take like the n-fold derivative of this, like the partial with respect to each of these components. The derivative will annihilate all these integrals, and you'll be left with this, right? Maybe I should write that out. So if you differentiate the CDF of the vector in the continuous case, once with respect to each of the components, okay, that is just from the fundamental theorem of calculus, you get the density back. Sometimes you'll hear people say a random vector is continuous if its CDF is continuous. Or in the random variable case, a random variable is continuous if its CDF is continuous. That's wrong. Okay, that's not true. I mean, it's a definition, so I guess it's not really wrong, but the properties that random variables are, universally, that continuous random variables are universally assumed to have do not hold if you define continuous random variables that way. Nonetheless, I know of textbooks that define it that way. Okay, it's not continuity of the CDF that matters. Okay, it's more tied to differentiability than continuity, actually. Okay, this is the acid test right here. Okay. It's kind of a subtle point. It's not going to crop up in this class, but I thought I'd point it out. Okay, so we have these three objects that like completely describe a random vector. The CDF. If the random vector is discrete, there's the PMF. If the random vector is continuous, you have the PDF, right? The CDF is the hardest to work with of the three, probably because it's so general. Okay, the other two are more specific, more specialized, and therefore easier to work with. So I'll give you an example of that right now. The chance that some continuous random vector x falls in A, you can write as an integral over A of the density. Okay, so that's an explicit formula for which there's no analog with CDFs. So as an example, let's take n equals 2 and consider the following CDF. Okay, here's a very concrete CDF. So it's min of min of max of x0 and 0 and 1 times the same thing with x1. So times min of max of x1, 0, and 1. Okay, there's my CDF of the random vector x. Equivalently, you can think of it as the joint CDF of the two random variables x0 and x1. Same thing. Okay, suppose I want to compute a probability like this. What's the chance the sum of the two components is less than or equal to 1? In principle, this is computable. Okay? In principle, this completely describes the random vector. Okay? In principle, any probability you want to compute involving the random vector, you can compute knowing this information. Okay? In practice, good luck. I mean, it's doable. Okay? But it's kind of awkward. On the other hand, if I differentiate this, what happens, the derivative is zeroed out in these places where the CDF is constant, okay? And the derivative of these are both 1. So all you get is a density that's 1 if both components are between 0 and 1, and 0 otherwise. Okay, all I did was really apply this formula to this. So all we have, that abstruse formula right here, okay, all we have is a square dartboard, okay, and then a player that throws the dart and is guaranteed to hit the board, but is equally likely to strike anywhere on the board. That's all this distribution is, right? Okay, so you can get that out of the CDF, okay, but it's a lot easier to work with this. In particular, can we answer this question though? What is that probability? It's exciting, I know. So you can use this formula right here, right? Once you have the density, you just integrate over the realizations you care about. Realizations we care about are the ones where x0 plus x1 is less than or equal to 1. What does that set look like? Superimposed on top of this is what? It's a triangle, like that, right? I mean, okay, it's not technically this set here is like everything below that line, right? Okay, so if you integrate the density over that set, you get half, right? Okay, you can get that information from this. I mean, one way is to go through this way. It's also possible to do it directly. Okay, the point is that it's a lot easier to work with densities and PMFs when it's possible to work with densities and PMFs. Okay, it's not always possible to do that, but usually it is, and when it is, we do it that way. Okay. So next, let me talk about moments. Okay, so these objects that describe the random vector, it's CDF, it's PMF, it's PDF, okay? These are very informative objects. They contain a lot of information. You can compute any probability you want involving the random vector if you have its CDF. You can compute any probability you want if you have its density. Okay, so these are rather rich, informative objects we're talking about here. They contain a lot of information in them. In some ways, they actually contain like too much information, okay, in the following sense. First of all, they can just be rather abstruse and hard to understand, like this. It's hard to look at it and just kind of immediately understand what this random vector is doing. Okay, in this case, we have an out here. You can take the density, and then it's clear what's happening. Okay, but there are cases where the density itself is very complicated and kind of hard to understand. So that's one issue. Okay, the other issue is because these things are so informative, they can be hard to learn in practice. Okay, so in your probability class, 3100, whatever, I don't know. Who here took ECE3100 at Cornell? Okay, so a lot of people, and we have some MN students, transfer students who did not. In a class like 3100, okay, you're just given the distribution, right? Okay, the problems always say, consider a random variable that's exponential with parameter mu, right? Consider a Gaussian random variable. Consider a uniform over this set. Okay, the distribution is always given to you, right? Or you're computing it from information that's just handed to you. Okay, out in the real world, no one hands you the distribution. With ComCloud, we have noise in the ComCloud. That noise is stochastic. It's going to present a problem for us. Okay, we need to deal with it. What is this distribution? The wave files don't come with a tag on them. Say, hello, I'm Gaussian with zero mean. It'd be great if that was the case, right? But you just get numbers. You just get a wave file. It's just a string of numbers, okay? And we need to attach a distribution to that in order to do analysis and design and stuff. Okay, and so we have to try to craft a distribution like from data. Okay, and the trouble is these distributions, they're so rich in information that it's hard to really fit them to data. It takes a lot of data to really learn distribution well. Okay, so there's sort of too much information in the sense that they can be hard to grasp, and also they're hard to learn just because they're so rich and have so many degrees of freedom in some sense. Okay, so for both of those reasons, we often revert to using moments. You can think of moments as just summaries of a distribution. Okay, so like one number that summarizes something about a distribution, like where it's centered, how spread out apart it is. Okay. All right, so the first moment we'll consider is one you've no doubt seen before. So the mean, also called average, also called expectation, also called expected value, also called literally the first moment of, and I'm going to do this for random variables first. Okay, we'll talk about moments for random vectors shortly, but first moment of a random variable x is, so we write like this, expectation of x. And let me write it down here. So in the continuous case, you just integrate x against its density. And in the discrete case, just sum x against its PMF. Like that. Okay, this is one number. It basically tells you where the distribution is centered, like what number it's centered about. You can make that precise actually. Like suppose you had a discrete distribution that had a few mass points, like that. So with probability whatever this much, it takes that value. Probably that much takes that value, and so on. Okay, then expectation of the random variable will be this point about which that teeter-totter would perfectly balance. And I just, honestly, it's interesting. I had taken this fact for granted for many years. Like, I teach 3100s. Okay, yeah, it balances around the fulcrum. Center of mass, center of gravity. Okay, and at one point I asked myself, how do you prove that actually? Like, how would you show that the mean is the center of mass? I thought, wow, this is probably some physics thing. I had AP physics in high school, and I took no physics in college. Zero. I AP'd out of it. They don't do that anymore, I don't think. Wisely, okay, I can tell you my physics background ended up being very weak, actually, because I never had any college level physics. So I assumed it was some physics thing I just didn't understand. And then I realized later it's like immediate, actually, because all you do, if you want to show that this point is the center of mass of that distribution, all you do is write down the definition, okay? Move the expectation over inside the sum. Like this. Use the fact that when you sum over x of px, you get 1, right? So this one implies this one. Yeah? You with me here? A implies B, yes? You want me to show that? Okay, we're going to need to be a little more interactive here, okay? Okay, so I can either prove A implies B or we can proceed. Who wants me to prove A implies B? No shame. No shame in doing it. 1, 2, 3. Okay, all it takes is 1. All it takes is 1. Okay, We're good with A, right? This is the definition of E of x. When you write E of x for a discrete random variable, it means that, okay? So now take the same formula, and I'm going to use the fact that when I sum up over all different values of the PMF, I get 1. Right? People okay with this equaling 1? You know, it's like you add the probability that the coin is tails plus the probability the coin is heads, and you get 1. Right? Or you have the chance that the die is 1 plus the probability that it's 2, 3, 4, 5, up to 6, you get 1. Right? Okay, so I've just multiplied by 1 here. Right? Now, move this inside. Okay? And then subtract both sides by this quantity. And if you combine them, you get that. You have the x from that was originally here. You get minus E of x. That's what was on this side. And that's 0. Okay, so you've got to use the fact that PMF sums to 1. Beyond that, it's just algebraic manipulations. Okay, so that A implies B. And B implies that the mean is the fulcrum about which this teeter-totter stands still. How do I see that? Do you have anyone who's not ECE in here? Do you have any mechanical engineers who? I imagine your typical mechanical engineer will just like read this right off. No? Okay. Guys familiar with torque? Yeah? All right. Here's a quick mechanical engineering lesson for you, right? So, you know, the torque is like the force times the distance from the rotation point, right? So here's my rotation point. For each mass point, right, this is the force. That's the amount of mass there, right? This is the distance from the rotation point. So this is the contribution to the overall torque from one of these mass points. You sum them all up. The net torque is 0. So it doesn't spin, right? That's the proof. It's like the definition with, you know, this calculation, and then you just got to interpret it in terms of torque. Okay. Yes, expectation. When I teach 3100, I do a full 75-minute lecture on just expectation of x and how to think about it. Okay, there's a lot to say about it. It's a useful moment, okay, because one number kind of gives you a sense of the point about which the distribution is centered. That's useful to know. Since it's just one number, it's a lot easier to estimate from data than the full distribution. Okay, if you get 44,100 samples out of ComCloud, okay, you can just like sum them up, like take the arithmetic mean of them, okay, and get a reasonable handle on what the expectation of the noise is. Okay, whereas you might not have enough data to really estimate the full distribution completely, including all the tails and everything. But the mean you can estimate from relatively little data. Okay, so that's one moment. Next moment's the variance. That gives us a sense of the spread. So the variance of a random variable x is, we write it as var x, like this. And it's the mean of another random variable, derived one. It's the mean of the random variable minus its mean quantity squared. Okay, so it's like looking at, on average, how far you are away from the mean. Okay, so in that sense, it's giving you a measure of the spread. Okay, so this would be, in the continuous case, x minus the mean squared, integrated against the density. In the discrete case, x minus its mean squared summed against the PMF. Okay, so the variance complements the mean. The mean tells you, the point about which the distribution is centered, and the variance kind of tells you how far you are away from the mean. Okay, note one fact. The variance of a random variable is 0 if and only if. It's my abbreviation for if and only if. Okay, not a typo. If and only if the random variable is just always equal to its mean. So it has no spread to it at all. It just always takes one value, and that one value therefore must be its mean. Okay. I think one direction, like this direction is easy. If this is true, then the variance is 0. That follows directly from here. You can also show the reverse direction. It's not that much harder. The variance is really nice to work with theoretically. When you're doing calculations, okay, the variance is a kind of a nice moment to work with. Satisfies lots of nice properties, easy to compute, and so on. You can also learn from data quite effectively. But when you're operating with data, like when you want to talk about the variance of like a distribution from a data set you have, okay, it's actually not very nice to work with the variance. To talk about the variance of the samples. Anybody know why? Why would I say that? To me, this is the test of whether people have kind of like used variance, like used probability kind of out in the real world to kind of operate in data, or whether you've only used probability kind of in a classroom context doing calculations. Okay, so once you use these concepts out on real world data, you kind of very quickly see the limitations of trying to use variance to talk about like spreads of actual distributions. That was a hint. No dice. Okay, so lab 1. Okay, you send silence in. You get 44,100 samples of noise at the receiver, right? Okay. You can estimate the variance of that distribution. Okay, estimate the mean first, you know, and then just take for each sample, take its distance from the mean, square it. Okay, take arithmetic mean of that. That will give you a good estimate of the variance. I can tell you roughly what you get. Roughly, you get something like 10 to the minus 10 volts squared for lab 1. That's roughly what you get. Do you find that to be a helpful quantity? I do not. I don't know what volts squared even is. I mean, you can define volts squared, but how do you think about that? 10 to the minus 10 volts squared, is that big? Is that small? I mean, 10 to the minus 10 is a pretty small number. So presumably that's kind of a small thing, but you know, volts squared, like, what's the issue with variance?
The units.
Yeah, so if the units of x are meters, the units of variance are meters squared. Thank you. Meters squared, right? And that's just kind of hard to think about, you know? Okay, you know, like you say about the average height of like a female in the U.S. is, okay, this is going to be kind of hard for me to try to do on the fly, but okay, there exists a planet, let's say, where the creatures, you know, have a mean height of 1 meter, and the variance of that is like a 1/4 meter squared. And it's like, okay, so how much spread is there about it, right? I don't know how to think about that. Okay, so when you're trying to understand intuitively how much spread you've got, you don't use variance. You probably know what you do use. You use the standard deviation. Okay, just the square root of this, okay, which just kind of brings it back to the unit system that you're familiar with and is easier to think about. Okay, so the standard deviation of random variable x is just simply the standard, we write it as STD of x. Okay, and it's simply the variance of x square root. Okay, variance is always non-negative, so you can always take square root of it. Great. Standard deviation will be 0 if and only if the random variable has no spread. It's always equal to its mean. And the nice thing about it, it has the same units of x. Okay, so when I say now that like the standard deviation of the noise in the comm cloud when you send in silence is about 10 to the minus 5 volts. Okay, whereas the signal is about 1 volt. Okay, to me that's something I can kind of understand now. Okay, so I can send a signal between like 0 and 1 volt. Okay, and the noise is kind of on the order of 10 to the minus 5 volts. Okay, that's something kind of intuitive I can now picture in my head. When I phrase it as 10 to the minus 10 volts squared is the variance, which is saying exactly the same thing, okay, it's kind of hard to reason that through. Okay, so that's all for random variables. What about vectors? Say moments of random vectors. Okay, so let's start with the mean. The mean of a random vector, x, just defined as follows. So we use the same notation, E of x. Okay, it's mean and expectation, expected value, average, first moment. Okay, all the same terminology we use here. And it's just the component-wise mean of each of the components. Okay, so there's a lot of brackets here, like that. This looks dangerously circular, right? I'm defining this E operator in terms of the E operator. Is that bad? Is this a circular definition? Yeah? Okay, am I defining what I'm trying to define in terms of what I'm trying to define? If so, then I haven't defined anything. I just have like a little circle of logic. Okay, why not? I'll give you a clue. Why is this not circular? I'm not defining this in terms of itself. I'm defining this in terms of something I've already defined but happen to use the same letter for, right? Okay, I'm defining mean of a random vector in terms of means of random variables, which we already defined. It was right up here, right? Okay, so if you can compute the mean of a random variable, you can compute the mean of a random vector. Okay, you just compute the mean of each of the components, take all those means, put them in a vector. That's that. Okay, and you can show, you can arrive at the same formula the usual way. So just integrate x against its density, or sum x against its PMF. This is not good. Like that. Okay, using any of those formulas, you can verify that notation is linear. So like factors get pulled out. So if you want expectation of a matrix A times x, so underline is my notation for matrix. Matrix A times x. Okay, you can show this. All right, so that's mean. What about variance? Okay, so probably the first definition that would pop into one's head for defining the variance of a random vector would be to just like mimic this. Just take the variances of each of the constituent random variables, put them in a vector, call that the variance of the vector, right? You can certainly do that. You can just define variance of x to be like variance of x0, variance of x1, variance of xn. Okay, you can do that. You can define such an object. Okay, there's nothing wrong with it. It's a definition, so like, it can't really be wrong. It's not really very useful, though. You know, whereas variance of a random variable is quite useful, variance of this is just a very pragmatic comment I'm making here. Okay, in practice, this object is just not very useful. Okay, and it turns out like you really need more than just the constituent variances to really compute stuff about the vector. You need the covariances as well. Okay, so let's define that. So the covariance between two random variables x and y is, simply write it like this, cov for covariance, x, y. And it's just defined to be expectation of x minus its mean times y minus its mean. Like that. Okay, so some notes. Covariance of x with itself is what in words? The variance of x, exactly. Covariance of xy is the same thing as covariance yx. So it's commutative, symmetric in x and y. That's clear here. If the covariance is positive, then we call these random variables x and y positively correlated. If the covariance is negative, we say negatively correlated. If the covariance is 0, we call them uncorrelated. Okay, and the way to think about it is as follows. So covariance is like the expectation of a certain random variable, a certain derived random variable, right? It's expectation of x minus its mean and times y minus its mean, right? So if the covariance is positive, that means this random variable inside the expectation tends to be positive, which means, you know, when this is positive, then this tends to be positive, and when this is negative, this tends to be negative, right? So it's like when x is bigger than its mean, then y also tends to be bigger than its mean. When x is less than its mean, then y also tends to be less than its mean. So they're moving together, right? When one is big, the other tends to be big. If they're negatively correlated, then this random variable tends to be negative. So when x is above its mean, y tends to be below its mean, and vice versa. And if they're uncorrelated, then it's just kind of incoherent. X and y are independent. What can we say about the covariance? 0? Yep. Okay, so, you know, in general, when u and v are independent random variables, just like a fact from your probability class, when u and v are independent random variables, then expectation of the product is the product of the expectations. Okay, so if x and y are independent, then x minus its mean is independent of y minus its mean. This becomes expectation of x minus its mean times expectation of y minus its mean. Those are both 0. The whole thing is 0. Okay, the converse is not true, however. You can have uncorrelated random variables that are dependent. So there's kind of a gotcha there. One bit of notational shorthand. We're going to write this a lot. X and y are independent. Okay, it's a lot to write. So we need a shorthand for it. This is the shorthand we'll use. Okay, it's like an upside down capital pi. All right. So you might have seen this for orthogonal. It's kind of like in that style. Okay, upside down pi. So it's like orthogonal but with 2 lines up. Okay. So to define like the equivalent of variance for a random vector, we're not going to just take the variances of the constituent random variables. We're going to throw the covariances in as well. Okay, we'll get a much bigger object. It'll be a matrix instead of a vector. and that matrix will tend to be a lot more useful for us. Okay, so here's the definition. So the covariance matrix, what we call it. So we don't generally talk about the variance of a vector. Okay, that term we just don't really use. Instead, we talk about the covariance matrix instead. Covariance matrix of random vector x is defined as follows. Write it like this. Underline because it's a matrix. Subscript for the random vector you're talking about, like with the CDF. Same thing. Okay, and it's a rather large matrix. And it's basically like all possible covariances. So you take covariance x0, x0, covariance x0, x1, covariance x0, xn minus 1. Covariance x1, x0, covariance x1, x1, covariance x1, xn minus 1. Okay, I guess I had been writing arrows on the vector even when I evaluated at a particular time step, right? So let's put arrows on all of these. Okay, and so on the last row is covariance of xn minus 1, x0, covariance xn minus 1, x1, covariance xn minus 1, xn minus 1. All right, it's all possible covariances thrown in a big matrix. Okay, the ijth entry is the covariance between xi and xj, right? Tell me about the diagonal entries. They're the variances. Okay, so that vector I defined at the beginning with the variances, that's still here, just along the diagonal. Okay, and I've populated the off diagonal with all possible covariances. Okay, this is a much more useful object than just the vector variances. Let me try to convince you of that with the following little calculation. So suppose n is 2, so you just have a two-dimensional vector. So x, 0, x1, like this. Suppose I want the variance of the sum. So consider a derived random variable obtained by just adding the two components. Okay, can I compute this from the variance of x0 and the variance of x1 alone? Let's see. We can compute this. So the variance of the sum, this is by definition expectation of the sum, right, minus its mean squared, right? Variance of u, expectation of u minus its mean squared, right? Okay, expectation is linear, so let's take the expectation through. like that. Okay, so all I did was I pulled the expectation through and then I just rearranged, so I put the random variable next to its mean. Yeah? Okay. So expand the square, but like keep the random variable married to its mean. So treat this as an object and treat this as an object. Okay, when you expand the square, don't blow it up into like 16 different terms. Okay, treat this as an object, treat this as an object. So first one is going to be expectation of x0 minus its mean squared. The other one will be x1 minus its mean squared. And then I really wish we had bigger boards. So continuing up here, the cross term. Okay, I guess I have a plus sign there already. So you're going to get 2 times expectation of x minus x0 minus its mean times x1 minus its mean. Like that, right? Okay, I just expanded the square. So this is the first thing squared, the second thing squared, and you have 2 times the cross term. All right. Inwards. What's this? Variance of x0. Variance of x1. Is that one? It's the covariance of the two, right? This is variance of one, variance of the other, plus twice the covariance of the two. Okay, so if I want the variance of the sum, and all I have are the marginal, the constituent variances, then I'm out of luck. Okay, you cannot compute the variance of the sum merely from the individual variances. You also need the covariance. Okay, and this in a nutshell is why the vector of variances of the individual variables is not very useful, but when you throw the covariances in, then suddenly it does become useful. Okay, because in this case, kx, in this two-dimensional example, the covariance matrix is the two variances along the diagonal and then the covariances, or the covariance on the off diagonal, right? Notice I've written 0, 1 here instead of 1, 0, right? That's safe because they're the same thing. You can put 1, 0 here if you want, but covariance is commutative, so these are the same no matter which way you write it, okay? So if you want the variance of the sum of these two variables, if all you have are the individual variances, you're out of luck. If you have the covariance matrix, though, then you're in good shape, right? You have everything you need to plug in the formula. In fact, okay, observe the variance of the sum is actually the sum of everything in this matrix, right? It's this variance plus twice the covariance, right? Well, looky here. If I just add it all up, I get variance plus twice the covariance, right? That's not a coincidence. Okay, that always happens. So here's our first theorem in the class. Okay, so I use the word fact and theorem differently. Okay, theorem is something that we will prove in the class. Either I will prove it, okay, in lecture, or you will prove it as a homework problem. Okay, but we will prove it as part of the class. A fact is something that's true that we're not going to prove. Okay, I'm not going to prove it, and it's not going to be a homework assignment. Those you just have to take on faith. If you're curious, I can point you to where you can find proof somewhere else. Okay. Another way of thinking about it, if you want to think in terms of like, exams, so facts, you're not really responsible for understanding why they're true, just knowing them, you just have to know them. Theorems, okay, the why they're true is like part of the class. Okay, so I'll just state this, and we'll prove it next week. If A is a deterministic vector, then the variance of A transpose X, think of this as like a linear combination of the components of X, okay, is A transpose KX A. Okay, so in particular, if you take A to be all ones, then you're just summing up all of the components of X. The variance of all the sum of the components ends up just being the sum of all the coordinates in the covariance matrix here. Okay, all right, so we'll leave it there. So next week I'll prove this. We have a little bit more to do about covariance matrices, and then we'll pick up with Bayesian detection. Okay, so I have office hours right now if you want to chat about anything. Otherwise, I'll see you tomorrow at the CommCloud recitation.